Yes, it is one of these days. It is, of course, a letter from Florence. Let's see what Florence has to say today. Well, some components have fallen out of the letter. It says, Dear Connor, President Trump has placed an order with Lord Syrup for a 2-bit countdown circuit. Please help. Specification 1. When the countdown reaches 0, it stays at 0. And 2. If the countdown is not yet 0, it goes down by 1 each tick of the clock, unless the abort button is pressed, in which case the count goes back to 3. I shudder to think why President Trump wants this circuit. Anyhow, there's a PTO, so we better read it. It says, before I could finish the circuit, Lord Syrup sent me to deliver the abort button to the Pope. This is how far I got. And then there's a circuit diagram. So you can finish it, can't you? So we better try. What can we see? We can see we've got a D flip-flop, which is labeled, whose output is labeled Q2. I guess that's going to be the 2s for the counter. And we've got a JK flip-flop, whose output is labeled Q1. That's going to be the 1s for the counter. And then what's missing is the control circuitry for both of those two. And you can see that the controller for D gets the current signal from the abort button and the current state of both flip-flops. Whereas the controller for JK gets the abort signal and only the current state of the other flip-flop. Now, that should be perfectly normal by now. The control circuitry for a JK flip-flop never needs to see its own state, because it's always possible to use the control signals to say what the right thing to do is. So, we've been handed these bits and pieces. We've got a mux, we've got and, we've got or, and we've got not. What do you think? What should we do? Any suggestions for how we should solve this problem? That sounds like an excellent suggestion. Let's make a truth table. So, let's figure out what we're going to need to put in this truth table. Where are the pens that are the pens? Here are the pens. Right. So, we will need to know the current situation. So that's going to be, we'll need to know whether the abort button is being pressed, and we'll need to know the current value of the count. And what do we need to determine? Well, in the first instance, we'll need to determine what the counter should be next. So we'll want to say what is Q2 of t plus 1 and Q1 of t plus 1. And then later, we will want to figure out what signals to send to the flip-flops, right? We actually need to figure out what D2, J1, and K1 will be. Okay? Now you know, I hope, the way D flip-flops behave, that the Q2 of t plus 1 column will tell you exactly what the D2 of t column has to be, because that's how a D flip-flop is controlled. Whatever you want to come out at time t plus 1, you better put in at time t. It's a delay flip-flop. Okay? However, for Q1 of t plus 1, that's going to be controlled by these J and K signals. So we're going to have to figure out what they are. Let's have columns for them as well. So that's J1 of t and K1 of t. Okay, and we'll figure them out in a moment. Alright, so let's get cranking. I'm going to draw these ones big. And these ones small. Okay, so, I don't know. Now we have to understand the rules, right? Step one is to fill in these two columns just by doing what the rules tell us. So, what are the rules? Rule 1 says when the countdown reaches 0, it stays at 0. What does that tell us about the truth table? If we number the rows of the truth table from 0 to 7, according to the entry in binary, which rows do we now know the correct behavior for? Is there anybody in there?
0.
We know row 0 is one case where the countdown is at 0. So that's good. We know we need to, countdown is 0 here, it stays 0. Are there any other rows that we know?
1.
Well, just from the rule that says when the countdown reaches 0, it stays 0, we're not there yet, because the countdown isn't at 0 yet.
4.
Row 4 is the other row where the countdown is already at 0. So there it stays 0 as well. Okay, what's next? If the countdown is not yet 0, it goes down by 1 each tick at the clock unless the abort button is pressed. Okay, so we now know what should happen in the other 3 rows in the top half, where the abort button is not pressed, but the countdown is not yet 0. So, okay, on this row, what's the countdown currently? Do all shout at once. If the countdown is currently 1, what should it become? 0. If the countdown is currently, what's this? 2, it should become. And if the countdown is currently 3, what should it become? 2. Okay. Then the rest of rule 2 says, unless the abort button is pressed, in which case the count goes back to 3. Okay? So that tells us about the rows where the abort button is being pressed, but the countdown is not currently 0. That's to say, it should go to 3. That's 3. All right. Is everyone happy with why this truth table is the way it is in the first place? Why we chose these columns? And why we filled in these columns with these values? Just by following the rules. So we have now figured out the behavior that we want the circuit to have. Now it's up to us to do the electronics to figure out how to make that. Well, we need to do a bit more calculation. Are we good for, if you look at this column, we try and make the circuitry for D2, we've got these bits and pieces here. Do you see anything in the D2 column that's That's this column that might make these components useful. Yeah, you can see those things, yeah? If only we could cut the problem into two halves, controlled by the abort button, it would become really very easy. How do we cut the problem in half? With the mux. Okay. I think we're ready to go here on the D side. We're going to stick in a mux here, controlled by the abort button. Okay? And then we'll get two separate inputs, one for when the abort button is 0, the other for when it's 1. When the abort button is 0, what calculation should we do? We need to say, what calculation of the other two are we doing? It's AND. And when the abort button is 1, what calculation are we doing for the other two signals? Yeah, that's this truth table here, that's OR. Okay, we've spent a lot of our hardware already, so we better hope that the other part's easy. Let's get back to our truth table. Is everybody happy with how this got to be the way it is? I mean, the mux should have been a big clue to consider chopping the truth table in half. Okay, but in extremis, you've basically got to make a circuit that does this. It's an ordinary circuit construction problem. Okay, so let's get back to J and K. How do we figure these things out? Remember, this circuit gets only A and Q2. So it's got to explain how to instruct the flip-flop to update. So what we've got to do is look at the behavior of the flip-flop in each of the 4 cases. So when A is 0 and Q2 is 0, we go from 0 or 1 to 0 and 0. So what are we needing to do? We need to reset the flip-flop. How do we tell the flip-flop to reset? Send a 1 to K and a 0 to J. Okay? Everybody cool with that? We saw the behavior we wanted, we chose the signal that does that. So we're using the characteristic table for JK backwards. Okay, next. In the 0-1 situation, this is the behavior we want to happen. What's going on there? Yeah, we're toggling the flip-flop. How do you tell the flip-flop to toggle? What should we send in on J and K? 1-1. That's what tells the flip-flop to toggle. Okay, next one. This is what's happening. What's the flip-flop doing? It's staying the same. How do we tell the flip-flop to stay the same? 0, 0. And finally, what's the flip-flop doing this time? It's setting. Okay, so how do we tell it to set? 1, 0. Okay, so now we have the truth tables for the circuits that we need to build. Can anybody suggest how we build the circuit for J? We're computing J and K from A and Q2. What do we need? Wire. We're computing, we want to wire Q2 into J. All right? So that's just that thing, yeah? Okay. How about K1?
Not A.
It's not A. You can see every time K is 1, A is 0. When K is 0, A is 1. So we can compute K by not A. Oh, that's the shut up music. So there we are. We have a NOT gate left. So let's use it. There we are. We have built Donald Trump's countdown circuit, which will reach 0 if it is not aborted really rather frequently. So let's hope His Holiness takes his responsibilities seriously. I'm sure the abort button could be in no better hands. Okay, everybody see how we did that? Absolutely typical flip-flop question. Figure out the updates you want, figure out what control signals produce those updates, and then do the electronics to get those control signals. That's the way these things go. Okay, folks, have a great weekend. I'll see you on Monday. 1 minute papers in the box, please.